Myoungjean. She will talk about the boundary problem and applications.
Okay, thank you. Thank you for the introduction. So first of all, I must say this is not the first time I give a talk here. Moreover, actually, I gave a talk a few days ago. So when I got email from Professor Dong-Soo Kim, and when he asked me to give a talk here again, I was spending a lot of time thinking about whether I want to give a same talk or a different talk. And I decided to give a different talk to respect people who are willing to my talk for the second time. So now here's my second talk, which is a completely, probably a little bit similar to the last talk, but mostly different from the last time. So first of all, let me briefly say what was the topic of the talk I gave last time. So main subject was about transonic shock. So I spent some time to explain you what is the shock in a physical sense, and also I briefly explain how we mathematically formulate the transonic shock problem. After all, it turns out that the transonic shock problem is formulated as a free boundary problem. Moreover, when we add the word transonic, that actually gives us the mixed type PDE. Moreover, more precisely speaking, when I say mixed type, the transonic shock problem contains a nonlinear PDE system, which is hyperbolic in one part, but elliptic in the other part. So somehow I spent a lot of time about explaining how we define the transonic shock solutions when we especially talking about the solution to PDE, which usually requires the at least a continuous solution. But what do we mean by a solution to PDE with a discontinuity? So to somehow make the definition about the shock solution to PDE, I went back to the weak formulation of PDE, because after all, this problem comes from conservation law of the physics. So we used the original integral formulations, and from that we derived out the weak formulations, and using the weak formulation plus the integration by parts, we were able to derive out the shock condition, which must hold the shock. And part of the shock condition gives us the boundary condition to solve a solution in the elliptic part, and the other part of the shock condition was used to find out a shock, which is a free boundary. Now today, the focus of my talk is a little bit different. I actually want to go back to free boundary problem itself, because I just realized that I did not give you enough explanation between the difference between just the standard boundary problem and free boundary problem. Also, I want to just point out what this does do to general mathematical theory plus fluid dynamics. And moreover, after all, I want to convince you that free boundary problem itself has importance in both applications to engineering or fluid dynamics, to also it has importance to mathematics itself, in the sense that when we study various free boundary problems, it naturally leads us to study the various differential equations with a very interesting feature. And by studying them, we were able to derive out a very interesting theory, which actually can be applied to another problem in more general sense. So that is my aim of the talk today. So let's just go back to very elementary problem. So what is the boundary value problem? So when you actually go to the first class of differential equations, professor talk about initial value problem, boundary value problem, or just the PDE, just ODE. So just to make sure that everybody knows the meaning of the boundary value problem. So here is the Poisson equations. Laplacian U equals to F in certain domain omega. So here omega is given in the problem. So if omega given, And we know that, probably most of you know that this problem has a solution as long as the non-homogeneous part F and the non-homogeneous part of the Dirichlet boundary condition has enough regularities. For example, if F and G are smooth, plus the domain omega has a smooth boundary, we can always find a smooth solution. This is a very well-known theory. But what if the parts of the boundary is unknown? Then what happens? So what I mean by that, here is a domain omega with a boundary. If boundary itself is known, then there is no problem in finding solutions. But what if a portion of the boundary, so-called gamma, is undetermined? So what do I mean by that? So I will actually come back to that this issue later. Then this problem is no longer trivial. Because, well, even though we give Dirichlet boundary conditions, if we know where this condition must hold, because there is no trivial way to find out the solution by using standard theory. So in that case, this problem becomes free boundary problem. So after all, the meaning of a free boundary problem is the case where the boundary itself is moving, if we are talking about unsteady problem, or the portion of the boundary is unknown, then this becomes free boundary problem. Then in that case, what should we do? Well, then in that case, we have to find out the location of the free boundary plus the solution in the domain simultaneously. But this is not the arbitrary problem. Actually, this free boundary problem is very naturally derived from many physical phenomena. For example, there are many people who study so-called Stefan problem, which is basically classified as a phase transition problem. So for example, if we are considering an ice cube melting in the water, then we know that the surface of the ice cube will be changing by the time. So we want to find out the change of this interface. But in that case, as you can see, the density of the ice, if we say the density of the ice is 1, density of water is 0, we clearly see that there is a discontinuity across this interface in the density. Then one has to find out the interface plus for the change of the temperature in the inside of the ice cube. So this is one of the examples of free boundary problem, in the sense that the surface of the ice is moving by the time. Another example is water wave equations. So we know if we study the water flow, so I'm not an expert in this problem, so I shouldn't say too much. But when we study the water, for example, ocean flow, we know that the surface of the water is changing by the time from the effect of the, for example, the wind or other physical factor. So this also is the, one of the examples of the free boundary problem. The last example that I brought here is a shock problem, and this is actually one of my main interests in research. So what is the shock problem? So in general, shock is a discontinuity across which, when you consider fluid, we actually are interested in the density and velocity and pressure of the flow. And if we have the interface so that all these quantities are jumping, then we have a shock. So in that case, what we are interested is to find out the location of a shock plus the flow data behind the shock. So this is the shock problem. Well, it looks like that each problem has completely different feature. But one of the common features in this free boundary problem is that when we try to identify the location of a free boundary, we always come back to physical principle. And main physical principle is conservation law. So I can assure you, even though I'm not an expert of these two problems, for all these cases to determine the location of a free boundary, we always go back to conservation law. Especially for these two problems, we always look at the conservation of energy plus the entropy conditions. So these problems are related to physics, But then once we formulate the problem, we are back to the study of mathematics. So now I will try to spend a little bit more time on the shock problem. Then what do we want to do with this shock problem? So here's an example of the channel flow. Suppose that we know what happened upstream. So we know the solution here. Then we want to find out, and then, well, the shock happens for compressible inviscid flow, which means that we are talking about the flow determined by Euler equations. Navier-Stokes equation includes the effect of the viscosity and heat diffusion. And then if we have both effect, both viscosity and heat diffusion already smooth out the solution. So for that case, we do not expect to see a shock. But once we remove the effect of viscosity and heat diffusion, well, then we can expect to see a shock. So then, which means that we have to go back to Euler equation to see a shock. So now we are talking about the solution to Euler equations, which are written here. So the last time I spent a lot of time explaining what is the meaning of each equations. Now I will just assume that you already know the meaning, and I will just write down the equation as like here. So assuming that we know the solution upstream, satisfying this equation pointwisely, plus if we have certain condition at the boundary so that we can no longer have the continuous solutions, then we want to find out the location of a shock plus the solution satisfying the Euler equation pointwisely downstream. So that is the main statement of the shock problem. Okay, then how do we know where this shock happens? Again, then we go back to the physics, and we look at the conservation law, which are originally formulated as integral equations. And by using that integral formulations, we can derive out the jump conditions that this solution must satisfy.
There is an expression, what do you mean by P minus and P plus?
Okay, so here, the subindex minus means the solution before the shock. Subindex plus means the solution after the shock, because we have discontinuity. So we have to solve the Euler equation separately in each of the regions that we have a set of function. Combining all this, we have a shock solution. So plus usually means the solution after the shock. Okay, so I see, so many people probably do not have much experience in the shock study, so I brought some references that maybe you could try to read. So if you look at the reference about Levesque, there is one chapter contributed to the introduction of gas dynamics. They have this has very readable and approachable explanations, so I recommend this book for the introduction. And if you're interested in the shock problem, then probably the best reference so far is the supersonic flow and shock wave by Krang and Friedrich. So this reference is written a long time ago, but still it has a lot of problems to be explored in the future, plus a little bit more technical detail. And then if you're interested in the current research situations in this area, I also recommend boundary value problem for transonic flow. Actually, this has a little bit more new problems, and also there are some papers that I recommend you to read. Okay, so here, this Euler equation with a shock was suggested basically 200 years ago. But then there was no rigorous result for a long time. And basically, from this paper published in 2000, this Chenich, Kiffich, and Riverman first used the method of iterations to prove the existence of shock solutions. And then after that, there are some papers following. So I brought some interesting papers. So here the paper by Myoungjean and Feldman, they mostly study potential flow. So potential flow is the flow whose velocity field is given by the gradient of the scalar function. So if we use this formation, then we can simplify the Euler system a lot. It's somehow relatively easier to study the transonic shock. And Myoungjean, so Myoungjean himself and his student used a two-dimensional Euler system model to prove the existence of transonic shock in various cases. And this paper is one of those. And Myoungjean, also his collaborator, they, as I understand, they mostly use the isentropic Euler system, which means that the entropy for this model is assumed to be globally constant. In that case, also they can somewhat simplify the Euler system, and also were able to prove the existence of transonic shock in many cases, including the multidimensional cases as well. Okay, so far, what have been established? Well, first of all, I must say, as a person who's studying the transonic shock, all the theory developed from this study is not only useful in the study of transonic shock itself, but also it contains a lot of general mathematical theory. For example, when we study the transonic shock problem, the first thing we want to prove is existence. And to prove the existence, we cannot avoid to prove the existence of nonlinear PDE. And this nonlinear PDE is both hyperbolic and elliptic time. So always this study is related to the study of existence. And to prove the existence, well, since if you remember the Euler equation, since the system is nonlinear, and one of the way is to one of the way to prove the existence of solution to nonlinear PDE is to use linearizations. Once we linearize the PDE, we use the method of iterations. And using the iterations, we can prove the compactness. Using the compactness, we are able to find the solution. In that procedure, one of the main features is to use the regularity of the solutions. So existence theory naturally leads to the study of regularity theory. Plus, in the method of iterations, we always go back to the fixed point theorem to find out the solution to nonlinear systems. So always function analysis plays an important role. And so therefore, by studying this transonic shock problem, we are able to develop some of the functional analysis theory as well. And then recently, one of the very interesting improvement in the study of transonic shock is that in the study by Myoungjean and Daewha Wang and Marshall Slumrod, who recently visited KAIST. So those three people originally are studying the Euler equations in the formulation of fluid dynamics, and recently they were able to find out the connection between the Euler equation and isometric embedding theorem, which is one of the big problems in differential geometry. So isometric embedding problem is mainly, the main goal of this problem is to prove the existence of isometric immersion from an n-dimensional manifold to the Rn's ambient space. And as I understand, for a given manifold, if the Gaussian curvature is positive, then the equation becomes elliptic, and then many people know what happened in that case. But if the Gaussian curvature becomes negative, then the equation becomes hyperbolic, and then so far there was not many results known. But recently what these people do is to use the formulation of Euler equations from the fluid dynamics point of view, and they were able to rewrite the Gauss-Kodachny equation, which is a geometric equation, in the formulation of Euler equations, and use the method developed in the study of the Euler equation to show that there exists isometric immersion from two-dimensional manifold to R2 where the Gaussian curvature is negative. So basically, they use the method of hyperbolic PDE developed from the Euler equations to solve the geometric problem. So, yes. I'm sorry, R3. So for the two-dimensional Riemannian manifold to R3, where the Gaussian curvature is negative. So now people start asking, what if we have the Riemannian manifold where the Gaussian curvature is positive in some part, negative on the other part? Or what if the Gaussian curvature is 0 somewhere? Then one really has to study the mixed type equations, which actually naturally leads to the question whether we can use the method of transition problem to study this isometric embedding theorem for general Riemannian manifold. So this is one of the directions. So in US, actually, there was a conference for both of the people from the conservation law and differential geometry, and they were actually really start working together to find the connection between those two different areas. So this is one of the very sensational improvement recently. And also, most important thing is that the rigorous mathematical study of transition problem are really able to answer the questions which were originally coming from the fluid dynamics or some engineering. Because if we go back to 200 years earlier, people were just studying the fluid dynamics from the engineering point of view, and then they really start asking the questions whether the shock is possible or impossible, and they were all physicists. But then also recently, many people are studying this transonic shock phenomena by using numerical analysis. But when we do that, we have a lot of results actually. But the problem is that people just do not understand what this result means. So therefore, we could not avoid the theoretical study of this transonic shock problem. So people also have made a lot of progress in the last several decades. So we finally start being able to ask them the physical questions as well. Okay. So now, so far I told you, studying the transonic shock problem, which is one of the free boundary problem, gave us mathematical development. Plus, also this also contribute to another area in mathematics. Also, it contributes to the study fluid dynamics problem. Now, I want to go back to a little bit mathematical study and really give you some detail what was the general result we gained from the study of transonic shock problem. And here is the first example. So if you were here the last time, actually you already saw this slide, but I changed the theorem statement a little bit. So this picture shows the shock reflection problem. And let me again briefly explain what is the shock reflection problem. So given a symmetric two-dimensional wedge, when a plane shock is moving forward to the wedge, when this hits the wedge, if this angle is sufficiently large, then we see the shock reflection. And when this happens, near this reflection point, the reflected shock is almost straight. But then away from the shock, it starts curving. So this is the shock reflection problem. And then, well, first of all, we can explicitly compute this shock curve plus the state behind it, which we call the state 2. And this is given by, first of all, constant density, which we can compute by using the implicit mapping theorem, plus the Rankine-Hugoniot conditions. And also, we can compute the corresponding velocity. In this case, recently, Guichong, Chen, and Feldman prove the existence of a global solution of this shock reflection problem by using the potential flow. So again, in this case, the velocity field is given by the gradient of the potential functions. And plus, they also show the solution exists in self-similar skip. So in the picture we are looking at is self-similar variable, which means here we have two-dimensional space variable, which is basically self-similar variable, where this capital X is a real spatial variable. So they use this self-similar scheme plus the isentropy potential flow to prove that there exists a solution of the shock reflection global solutions satisfying this structure. Okay. Now the interesting structure of this problem is that here we have the curve, so-called sonic curve. And let me explain what happens over here. This straight shock is the hyperbolic shock, which means that the state behind it is a supersonic. So therefore, the equation of the potential becomes hyperbolic. Behind the curved shock, the state becomes subsonic, which means that the equation of the potential is elliptic. So when we look at this state across the subsonic state, we have the curve on which the type of the equation becomes degenerate. So therefore, hyperbolicity of the potential, the equation of the potential becomes degenerate. Also, ellipticity of the potential equation becomes degenerate. And in general, there is no general result about regularity of degenerate elliptic equation so far. So what we study in the collaboration with Chen and Feldman is to look at the difference of the potential for this state, which is the supersonic state, and then the potential in the subsonic state. And here the psi is basically the difference of these two potential. But then the equation of this difference is very interesting. So here x is basically the distance from a point from the subsonic side to this sonic curve. So as you can see, as we approach it to this sonic curve, we see that this coefficient of the second order derivative becomes 0. So we have this degeneracy. And moreover, we also have a little bit of nonlinear structure. But then we found out that this nonlinear structure is actually a key point to get the smoothness of the solution inside inside of this subsonic side. So what we prove is that the distance between those two potentials basically behave like the quadratic functions. And this means a lot of things. First of all, this means that this function is in C2 alpha for anywhere the exponent between 0 and 1. So therefore, for the elliptic, from the elliptic equation side, this function is smooth. Moreover, if you look at the second order derivative of this guy, second order derivative is a non-zero constant, which means that there is a jump of the potential in the second order derivative. Well, what does that mean? Well, the first order derivative of the potential is a velocity. So therefore, this result implies that there is a jump of the derivative of the velocity in the shock reflection problem. Even though this is not a shock, still this is classified as a weak shock. So we also find out that fact. Okay, then what can this theory do to other problem? The reason why we are very happy with this result is because of this degeneracy, where one of the important equations that people want to understand is Cavendish equations. So if you're studying this type of equations, we have two interesting equations. The first equation is the Cavendish equations. If x is a positive, then we have almost Laplacian equation. So this is elliptic. If x is negative, we have wave equation, almost wave equation. This becomes hyperbolic. So therefore, on x is equal to 0, this hyperbolicity ellipticity degenerate. Then we just lose the information. Also, the other equation are trichotomy equations. So this problem also has the similar degeneracy. So far, well, there are not many results known about this problem because of this degeneracy on x is equal to 0. So hopefully, we can somehow apply the similar idea which is used to obtain the theorem to study regularity of the solution to this type of the equation, Keldy's equations and trichotomy equations. And one other interesting fact is that here actually we took the advantage of this nonlinear structure. On the other hand, this problem is linear, so there is no such advantage. So this may imply that the regularity of this the solution to this equation may be worse than the regularity of a solution to this equation. So this may emphasize the importance of the nonlinearity of the equation itself. Or probably it's also possible that we may get something similar to this result. So actually I had a discussion with senior researcher about this problem, and he was quite optimistic about maybe we could use this idea to somehow get same results about these equations. But also there is opinion, maybe this nonlinearity is a really key point, so we could not do that. So maybe this is one way or another. So this could be also interesting problem to study in the future.
By the way,
Yes.
do you know why this is really a circle, the sonic circle?
Yes, so here this sonic circle that one can compute explicitly. Yes, this is here is why. When you compute this state is given by constant density ρ2, and then the corresponding potential in the self-similar variable has the following structure. Oops, maybe. Some constant. So here, u2, v2 is the constant vector. And we know that if the velocity is less than the sound speed, then we have the subsonic flow. If the velocity is greater than the sound speed, we have supersonic flow. But then what is this gradient? This basically becomes the equation of a circle. So that gives us exactly the circle on which this degeneracy happens. Okay, so next result, which I'm personally very proud of. So this equation, as you can see, the transport equations. If velocity vector field is constant, well, there is no problem in finding the solution of these transport equations. But then, when we study the transonic shock problem, we go through a certain procedure of iterations that makes this velocity vector field has a weak regularity, depending on the regularity of the domain we are studying. So in the problem that I studied, actually, this velocity vector field has a very weak regularity. Well, what do I mean by weak regularity? In order to explain that, I need to tell you how we generally solve these equations, just for your own interest. Okay, here the vector field V is known. Then what we do usually to solve this equation is the following. So this is the initial value problem, where we look at the system of ODE here, which gives us the characteristic. So here, given vector field V, so this is time axis, and this is a space axis. So given point x0, we solve this system of ODE, then we have integral curve, which is associated with this vector field V. But then, the solution of this transport equation is simply given by this formation. So what does this mean? If you want to know the value of your solution to transport equation E, what you do is to just follow back this characteristic and take the initial value of this solution E. Why is that? One can actually easily check this. Because if you differentiate this equation, considering x as a function of t, satisfying these relations, Then when you differentiate this with respect to t, you have 0 on one side because of this formation. So this is already constant. But on the other hand, if you differentiate the function on the left by the chain rule, you have this formation, and this follows. This satisfies the equation of characteristic ODE, which is the following. So that's how we solve the transport equations. Basically, use this characteristic ODE. So therefore, solvability of the transport equation is reduced to the solvability of ODE system. Then everybody knows that if V is a Lipschitz continuous in X variable, then you always have the unique solution. But if not, suppose that if V is merely continuous in X variable, then you still have solution by Peano theorem, but you do not have uniqueness. So here, well, when we study the transonic shock problem, which is a physical problem, we already seek a unique solutions. So just the solvability is not enough. We always want the uniqueness. But then in the transonic shock problem, unfortunately, the velocity vector field V is not Lipschitz continuous. So we have a problem. So we had to study a little harder to prove the unique solvability of these transport equations. Okay, so there is certain regularity restriction here. So what does that mean? When we look at the velocity vector field V, well, we allow, well, if this is bounded, then we have the V Lipschitz continuous. Then problem is solved. But then in our case, actually, we had to allow that the gradient of the velocity blow up as this approaches to the corner of the domain. So this actually means that if alpha is between 0 and 1, we have blow up of the gradient. So our velocity vector field is not Lipschitz continuous, but on the other hand, it had a certain blow up rate. But then we were able to show that. Okay. But then we were able to show that in that case, this characteristic ODE has a unique solution as long as it satisfies this blow up rate. So therefore, therefore we have the unique solvability of the transport equation when we have this condition satisfied for the velocity vector field. Okay, then what is the application of this theory to the OD theory? Here's the example. If you look at, well, this is really calculus. So anybody can understand this. If you have this OD, well, you know that you have more than one solutions, right? Just identically 0, or these non-zero solutions. So you have existence, but you do not have uniqueness because of this part. Because this function is not Lipschitz in the X variable. But then if you have this term, then this function satisfies this blow-up condition. So therefore, we can always have the unique solution. So this is just something in the middle of the this ODE, and then the similar ODE with a Lipschitz function. So we have something a little bit better. So in this sense, well, I believe that this theory also can be contributed to the ODE theory.
What is the main idea behind it?
Oh, so here the main idea is that using the L2 estimate of the solution, the idea is very simple. First of all, because of this condition, we have continuity of the right-hand side. So we have the existence. But problem is we may have more than one solution. So what we have to do is to measure the distance between two different solutions with the same initial condition. But then, well, this is a vector, so we have to measure maybe probably the distance squared. But then this is almost like dv times roughly speaking, this is almost like this. But then we integrate. Well, this is really a rough argument, but then we use that this function is in L2, in the time direction. Okay, maybe something is wrong. This is a derivative of the distance. So therefore, oh, so here, okay, so maybe, okay, well, suppose that x1 and x2 are scalar, just for convenience. But then I subtract these two ODE. So this becomes V of x2. Okay. But then I integrate this from 0 to certain time, say capital T. Okay. Then what I have here is so suppose that they have the same initial condition. Then I have x1 minus x2 of t is equal to, well, so probably I can rewrite this way. Okay, so what I do is the following. So if you look at the right hand side, so this is less than or equal to. Well, first of all, now we use the fact that dv.
What is the
Oh, the derivative of v. Yes, in x. Yes. So then we see that if we use this condition, we can show that this function is in L2 when you integrate with respect to time. Okay, so therefore we use the L2 estimate. So this is well, we can rewrite this as epsilon. We use the further inequality. Then this is a less than or equal to epsilon times the supremum of x1 minus x2 squared plus L2. Okay, I'm sorry, I do not remember this proof anymore. But here, the idea that I can tell you is that we use the fact that the gradient of the velocity is L2 in the time variable, and we use that to show. Okay.
So you want to show the contradiction, right? This is again less than the left-hand side.
Yes. So after all,
just some computation for what.
yes. I'm sorry that I do not remember the. Yes, maybe it's been a while, but the idea is to show that this is bounded by the distance between the initial condition times the L2 norm of this. But then if this is 0, then we have the distance between the two different solutions is 0. So here the main idea is to show that this is a finite. In order to show that, we use this blow-up condition because you can roughly say that this function, if you look at the geometry, so here is a time axis and here is a spatial axis. Given a point x, the distance between the point and the corner, say that this, the distance is about same as t. So therefore, if we say distance to the minus 1 plus alpha, this is about t to the negative 1 plus alpha, which is in L2 for any alpha between 0 and 1. Yes, so actually this plays a very important role in showing the unique existence of transonic shock solution for the divergent nozzle problem. The proof itself is very simple.
So, what is a corner? Corner is a line when he's...
Oh, so here the corner, I mean, is this point.
Just the point when x equals 0, y equals 0.
Yeah, so because when you look at the, say, Laplacian, so I actually have to say that in this domain, velocity vector field is given by the gradient of the potential. And then here, phi is almost the solution to the Laplacian of something in this domain. So we have the corner of the domain for this elliptic equation for potential. So that's actually weakens the regularity of the velocity vector field. So therefore, we actually, and then once we have the velocity vector field, we had to solve these equations to find out the entropy of the flow.
And in the statement of the proposition, so you mean the 2 has a unique solution E or 1 has a unique?
So here, if we have the unique, I'm sorry, so I actually must have say 1. Because
so
this...
Because the V is not reaches, even if you don't have solution for 2, you still have a solution to E, to 1, right?
Right, it's possible. So here, okay, so once I have the solutions again, I used a similar argument to show that the uniqueness of the solution E for the transport equations. I can go through the same argument. Suppose that I have one solution E1, another solution E2, then I take the difference, which means that I have to subtract this equation. But then actually I have to more or less go back to the same arguments to show the uniqueness of this solution to this characteristic ODE. So I still can show the unique solution to this equation. Yes, because, oh yes.
To the first one or second?
First one, yes.
Okay, but you don't know it yet. You don't, if the solution is unique for the ODE characteristic ODE.
Oh, okay, so it's a difference. So here, first of all, what I do is the following. Suppose that I have two solutions, E1 and E2. Then I can consider the solution E1 minus the E1 minus E2 as a solution to the same transport equation with the 0 initial conditions.
Yeah.
But then I have to show that the difference between E1 and E2 is identically 0. But then okay, but then, here's the point. So if I have the solution satisfying the transport equations, which means that this always satisfy this equation. It already satisfies these equations. But then now I want to know the value of E1 minus E2, where its initial condition is identically 0. To be able to say that, again, I go back to the argument of characteristic method. If I have the solution, when I have a characteristic, this value at this point must be same as the value at this point. as long as I have unique characteristic. So here the main point is that I do not have distinct characteristic for a given velocity vector field. Because once I have the solution, where the solution must satisfy the value at this point must be same as the value at the initial point. But then in this case, I have the initial data 0 everywhere. So as long as I do have the characteristic at this, the value at this point is already 0. So that's how I show that the uniqueness of the transport equation. So here the main point is to find out the unique set of characteristics, whether I have weak regularity of a velocity. And then I apologize for the not remembering the argument here, but I can assure you the argument is a lot simpler than you think. Okay, now the third general theory, which I was able to prove for necessity in seeking the unique existence of the solution for the transonic shock solution to nozzle problem, is a weak inverse mapping theorem. Right? I believe that this can be useful to undergraduate students as well. When you look at the inverse function theorem, the requirement is first of all, the function must be C1, and then the derivative of the function at a certain point must be invertible. Then you have inverse mapping. That is the standard inverse mapping theorem you know. But what if you know that you have continuous function, you have the invertible derivative at a certain point, but then you don't even know whether this function is differentiable at other points or not. The question is, can we still show that this function is invertible? It turns out that the answer is yes. Actually, I spent a lot of time on figuring out this theorem. Moreover, I'm talking about infinite dimensional inverse mapping theorem. For finite dimensional case, it turns out it's already known in this paper published in 1977. So statement is as follows. Suppose that you have a mapping F in a unipole, closed unipole in Rn. If this is continuous, and if, say, if is the derivative is invertible, then there exists, but this is a weak inverse mapping, so that when you put the inverse mapping to the right, this becomes identity. But you cannot put this on the left. So this is a weak version of inverse mapping theorem. And then the idea of the proof of this theorem was to use Brouwer fixed point theorem, which basically required that if you have a compact subset of Rn, and then if you have continuous mapping which maps the compact subset to itself, then you always have the fixed point. And I needed the infinite dimensional version of this theorem, so which I proved here. So, well, but when you look at the infinite dimensional case, now you need something more, because, well, general idea is that the infinite dimensional version of the Brouwer fixed point theorem is a Schroeder fixed point theorem, which means that you need a closed compact subspace of a Banach space. So when you have two Banach space with a compactly embedded subspace in each of the Banach space, if you have continuity plus the invertible derivative at one point, regardless whether this mapping is C1 or not, you can always at least find that right inverse. And actually that was more than sufficient to me. Of course here, the drawback of this theorem is that you do not have uniqueness, which means that given an image, you may have more than one pre-image. But at least you have pre-image. And that actually implied the existence of transonic shock solutions in the problem that I recently studied. But again, this also probably can be applied to other study in general, I believe.
You know the inverse, if the inverse is continuous,
also here okay, it's a good question. So for the infinite dimensional mapping in Banach space, if you have, when you talk about linear mapping, we have a bounded linear mapping. So therefore we have continuous as well. because when you say, when I say fractional differentiable, that means I have a linear mapping, which is bounded. And when I have the bounded linear mapping in infinite dimensional case, I automatically, so therefore this fractional derivative is continuous. It's inverse as well, of course. Okay, so I almost ran out of time, so maybe I have to skip this. I brought a toy model to tell you how in general we study the shock solutions. But I will just skip this one. Okay, I will skip this one as well. So now let me tell you what are the maybe current issue, one of the main issue in this area. One of the important but still widely open questions is whether when you have two different types of shock for the same situations, which one is more stable? Another question is what is the right way to say the stability? So this is one of the such questions, so-called parental conjecture. Here, the blue one is the obstacle, which is a two-dimensional symmetric wedge. When there is a supersonic flow given with a constant velocity and density, well, assuming that there should be no penetration of the flow to the wedge, we know that this flow must turn the direction somewhere, so that the flow direction is parallel to the boundary of the wedge. So therefore, we expect a shock in that case. And actually, by using the Rankine-Hugoniot conditions, which I keep mentioning during the talk, one can explicitly compute the solutions. So here, this curve, so here we have a u-axis, which means the x component of velocity, and v-axis indicate the y component of velocity. So by using the Rankine-Hugoniot conditions, which again is derived from the weak formulation of the Euler equations, given a supersonic flow, which is at this point, we can always compute the corresponding solution behind the shock plus the location of the shock. So here, if you fix the angle of the wedge, which is the half angle of this picture, we see that we have three intersections, which means that we have three different solutions. So this is obtained by mathematical method. But then we know that physically there should be only one, and which one is the right one? First of all, this point must be excluded because this violates entropy condition, which is a physical principle. So this cannot be solution. So then we have two solutions. Now, the problem is both solutions satisfy the physical principle. This one has the small, the distance, the difference between this solution and the given incoming flow, the gap is smaller. This one and this one has a bigger gap. So we call this one is a strong shock, this one is a weak shock. There are still arguments regarding whether weak shock is stable or not. So far, people believe that the weak shock is more stable. But then recently, there's been some opinion saying that, well, the stability really rely on the data you put at the infinity. So what I mean by stability here is that these two solutions have no problem in satisfying physical principle. But then when you start perturbing the data here, then which one will survive? There's been research showing that both cases can survive. So now another direction that I'm currently working on is to use the, again, unsteady scheme, like the reflection problem. So by using that, already it's known that there exists global self-similar weak shock solutions for certain case. Now I believe that there exists global solution in all possible cases up to this angle. Because if the angle of the wedge is bigger than this, then we see that there is no solution, which means now this shock must be detached from the tip of the wedge. Then the next question is then what happened near this corner? This is another interesting but difficult question that people have to study. So far there's merely no results known. But people, well, somehow try to understand this still recently. Because if you look at the airplane, the wing of the airplane is really has the small angle. So therefore, when there is an incoming flow, shock probably will be detached. So we really need to study in that sense, in the application point of view. So there are many issues. I'm sorry, I will just finish right now. There are other problems with Mach reflection, but I already mentioned a little bit about this Mach reflection in my last talk. So I will just finish my talk with interesting movie. So this is actually the video showing the Mach reflection. It goes really fast. Let me show you one more time. When the shock wave is coming, it hits the ground, then we see two shocks and the contact is continued in the middle. So this phenomenon really happens in the nature, but then there is no theoretical result, almost none. Okay. And then thank you for your attention.